All right. Cluster analysis. The aim of cluster analysis is to find groups in data or to find representative examples in your data. And we have seen use cases already. We have talked about instance segmentation. If you remember Anna Kreshok's talk, where we tried to partition an image into its constituent neurons. This was an example of cluster analysis, really. I can show you my first brush with cluster analysis. I was working at the time in a group on computational electromechanics. And they were looking at molecules, usually bigger ones than that, and integrating Newtonian equations of motion. Well, in silico, or the simulated time was nanoseconds, and it took weeks and weeks on the biggest compute clusters that ETH had at the time. And people had these configurations of these molecules over time. For example, of enzymes and their substrates, or your small peptides, or whatever. So you have these huge simulations, and then you try and find out, for example, what are the important structures that those molecules take over time. And here, for example, for this tiny peptide, these are a couple of the important structures that are being built over time. So cluster analysis, broadly speaking, helps you when you have reams and reams of data to try and make sense of it without any prior, class labels, etc. And there is, this is my description so far has been very qualitative, and accordingly, the problem is not, well defined. There are no class labels. Everybody can invent their own clustering technique and say mine is prettier than yours. And accordingly, there are a great number of techniques and also a great number of possible behaviors that these clustering algorithms have. So here, for example, from the scikit-learn website, you see a few toy data sets. Do not be misled by these toy data sets, okay? They are 2D. And, well, they have been, each of these toy data sets has been from left to right, or from top to bottom, has been designed, with a story in mind, or it was meant to highlight a particular property of a clustering algorithm. But, well, first of all, real data, it doesn't usually look like that. And secondly, in whatever intuition we gain here in these two-dimensional plots, will usually not carry us far when your real data has 100,000 dimensions nominally. The intrinsic dimensionality, as we know, is usually much, much lower. Yeah? So these plots, yes, they're interesting, but they don't really give us a good feeling for what these algorithms are doing in the high dimensional space. But anyway, let's have a brief look. What algorithms have we seen so far? We have talked about mean shift earlier this semester, and k-means. And k-means, or some variant of it, is here, and mean shift is there. You remember mean shift was building a density estimate and then clustering according to the modes or the peaks in this density estimate. And for example, with very elongated clusters here, like these circles, mean shift fails to understand that, well, the idea of the person who generated the data set was to say there are two clusters, and if we compute a density estimate, we apparently get a maximum somewhere here, and a maximum somewhere there, and another one over there. So mean shift wouldn't do well on this particular type of data. In general, I'm afraid, on those data sets, mean shift doesn't really shine. K-means, as we know, tries to find compact clusters, so it does a reasonable job here, does fine there. In the bottom, well, I guess there is not supposed to be any cluster, really. And so you can look at these a little bit and decide what is your own favorite. Some of these algorithms are a bit special. You see these here, they make explicit allowance for outliers. So one way to represent those clusterings would be to say, I make each of these small points a cluster by itself, but here these methods have an explicit notion of outliers, and they're here shown in black. I'll let you stare at this for a moment and decide what is your favorite column. Okay, and the winner is? Just shout whatever, what you like. Gaussian mixture. There is. Manuel, you have right? Okay. Good. He says Gaussian mixture. Other opinions? Spectral clustering. So Gaussian mixture is here. Spectral clustering is there. Which one? Okay, that's meant to be a D, so DB scan, okay. All right. Now, so this was the dimension of how much, or how good is the result. Then there is also a dimension of how beautiful is the theory. Manuel is sitting here, so I'm putting another, okay, for Manuel, for another one. DB scan in terms of beauty of theory, it's actually that. And so on, yeah. So, this is of course completely subjective, and I'm deleting it immediately. So the things that work well, unfortunately, are not always pretty, yeah. And then another dimension is, how long does it take? You see these tiny numbers in their inset in these boxes. You see that some of these methods are a lot faster than others. So if we look at speed, I think, this looks good. This looks good. Gaussian mixture looks good. All right. Good. So this was in terms of what the results can look like. Let's try and bring a little bit of order into the clustering literature. So we can have a taxonomy of clustering techniques. So a big distinction is whether we are hierarchical or flat. And both k-means clustering, if we specify k, or mean shift, if we specify a particular kernel, those are examples of flat clusterings. We get, boom, a set of clusters, and that's it. Hierarchical algorithms say, we're not really sure about, what is the right number k in k-means, or we are not really sure what is the good bandwidth to use for a smoothing kernel. And they hence build a family of cluster solutions which have the particular property that as we go up the hierarchy, so as we go to coarser scale, things that were clustered together will always stay clustered together. Yeah? So that's the definition of hierarchy. And then if we look at it computationally, we can build a hierarchy either by starting from atoms and collecting them into larger and larger units. So that would be agglomerative clustering. Or we can start from the top and divide recursively, which would be divisive hierarchical clustering. All right, and then there are many versions of how to do that. Generally speaking, agglomerative is computationally more efficient than divisive. So I think I'll put that in parentheses here. And then hierarchical algorithms are usually crisp, meaning a sample is either in one cluster or in the other, but not a little bit in both. Yeah? In flat cluster analysis methods, on the other hand, there are quite a few examples of fuzzy methods, or if we're lucky, even probabilistic methods, where this kind of distinction, which can sometimes be a bit arbitrary, is not made. So let's say we have just two clusters in our data set, close to the cluster centers, however we define them. You know, it's pretty clear that samples close to the one center, they belong to one cluster, close to the other center belong to the other cluster. But then we have samples in between, close to, you know, this ill-defined interface. And crisp methods still make an arbitrary decision. Like in k-means, for example, I'm closer to this code vector than to that code vector. Hence, I 100% feel I belong to that one. But you know that seems a little bit overconfident. And fuzzy methods like the Gaussian mixture model, they allow fractional memberships. So a sample can believe that it belongs 70% to that and 30% to that cluster center. That's what I mean here by fuzzy. Again, there are many methods, but the most important would be the Gaussian mixture model. Okay, and here I've mentioned k-means, and I've mentioned mean shift. And here we will look at single linkage, complete linkage, etc. There are many versions of how to define agglomerative clustering algorithms. All right. Yes?
Isn't mean shift also kind of hierarchical, seeing as that the points start to cluster together while the algorithm runs in bigger clusters, and depending on which time you stop, you have a different amount of clusters, and it follows the same rule?
So mean shift for a single bandwidth surely is not hierarchical, because you say I could stop at different times, but usually if I did all right, if I do calculate even with infinite precision with this adaptive step size that I gave as a postscript is the good one to use. Some clusters form a little bit earlier, or some points join their mode faster than others. That is correct. But yet this is not what I would call hierarchical. Let me show you a different picture. I think somewhere, yeah. I created a picture here of a few points and their density estimates just in 2D for various bandwidths. And you're saying for a single bandwidth, what if I stop mean shift early? I think this could be a useful method to identify outliers. It's not really what I would call hierarchical. Hierarchical would be more in the sense of going to coarser scales. And now that begs the question, if I now, let's say I iterate mean shift to the very end, but then I repeat this for a coarser scale, will this be hierarchical or not? And I think it is not, but can I give a proof? Yes. So the problem has been studied in computer vision in terms of Gaussian scale space, and there a famous example exists. This was courtesy of Tony Lindeberg. I'm trying to sketch now a density here with isocontours. All right, so we see that this thing has a single mode somewhere in the middle. But as I now, these are the contours of a density estimate here in 2 dimensions. But now as I start blurring more and more, this relatively thin ridge here gets blurred out into the 2nd dimension more than the dumbbells on the left and on the right side. And as a result, there can be new modes arising. Yeah? And this is why it is not hierarchical as I increase my bandwidth. Okay? All right. So I was trying, or many methods here make the argument in favor of hierarchy. So if you look at this set of points here, yeah, I would probably say, if these are, so we have a 2-dimensional feature space here, 10 points. Given so few points, I would probably say it's just a single cluster, or I would say it's 2 clusters, like here and there. Making any more detailed conclusions given so few points would be very courageous, I think. But sometimes there is even not a well-defined scale. Yeah? So we will talking a bit more now about hierarchical cluster analysis. And what I mean by no well-defined scale is if I asked you to cluster the world, if somebody gave the answer that our world is structured in terms of atoms, I would be quite satisfied with the answer. If somebody told me that, molecules are meaningful units, I would probably also agree. Then as we scale up from molecules, what's the next bigger cluster? I think it's planets. And then, another justifiable cluster would be at the scale of solar systems. And then we have galaxies. And then my knowledge of astronomy is very limited, but I think we have sort of galaxy superclusters or something. So, all of these are legit answers. And either we know what scale we're interested in, like we want to cluster at the scale of planets, and then this is fine. But sometimes when we get the data, we don't know yet what's in there. And we may want to have an open mind initially and look at all scales. All right. Now, if we do that, then we can build a so-called dendrogram. And what's beautiful here is that such a dendrogram, which I think means tree picture, such a tree picture, we can always draw it, no matter how high dimensional the real data is. And then we have here scale. We have down at the bottom the original observations. And then we see at what level different clusters merge. So for example, in single linkage cluster analysis, we always look for the closest members between 2 clusters in deciding if we want to merge them. So that means I initially Let's use here blue for single linkage clustering. I'm looking for the very shortest distance between any 2 points, and this is the distance between 2 and 3. And then the next shortest distance, as you can read off from the dendrogram, would be 4 and 6 that merge. And then the next shortest distance is between 8 and 9. And you know, at that scale, you may argue that actually that is a reasonable clustering. But if I now look at, you know, again, the shortest distance between any 2 points or 2 clusters, you know, I can go on. So I think the next one is 5 merging with 4 and 6, and then probably 7 merging with 8 and 9. Then 1 merging with 3 and 2. And then these merge. All right, now currently I'm at this level here. So I can threshold my dendrogram at any level. And at this level, for example, I would have 3 clusters. Now, the problem is, so we don't use, in hierarchical clustering, we are open-minded about the scale, but you still have to choose a distance metric and you still have to choose a clustering criterion. So if, for example, we choose complete linkage clustering, then we see that here sample 10. So here sample 10 was an outlier until very late, right? When I thresholded at this high level, sample 10 was still separate. Here, on the other hand, if we use the so-called complete linkage criterion, where we look at the biggest distance between any 2 points in 2 clusters, this 10 becomes merged with 4, 5, 6. So let's use, okay, let's say I'm using the blue threshold here, and now I'm using the red threshold there, which would group 7, 8, 9. It would group 4, 5, 6, and 10, and it would group 1, 2, 3. So you see, we get, unfortunately, quite different results here depending on the clustering criterion. Or unfortunately, fortunately, I don't know. But at least this has a huge impact. All right, so let's create some pseudocode for this. For agglomerative clustering here. I'm not writing pseudocode, I'm writing English instead. Okay, we iteratively merge the closest clusters. I'm going to elaborate on that in a moment. And update distance of the new cluster to all others. Okay, now we have many distance criteria. In the so-called single linkage clustering. We consider the shortest distance between any 2 points in 2 clusters. So this would be something like argmin over, let's say, I element my cluster 1 that I'm currently considering, and j element cluster 2. And then I'm looking for the shortest distance, ij. And then we have this other choice to make, namely what distance do we use here? So this could be a Euclidean distance, or it could be a slight generalization of the Euclidean, the Mahalanobis distance. In the Mahalanobis, in Euclidean, we say xi minus xj, xi minus xj. In the Mahalanobis, we allow to scale certain axes by some matrix here. Or I could have some LP norm. No? So if I say that this is xi minus xj, if this is the 2 norm, I could also use an LP norm here. So I could use xi minus xj. Some p where p can be any number, really. Or if you have structured data, then you may have more complicated distances that you consider between points. And single linkage clustering is a little bit special because single linkage clustering actually amounts to building a minimum spanning tree and truncating that. So if I truncate my dendrogram at a particular level, and if I use all right, what is the minimum spanning tree? If you have a graph, or here a set of points where this set of points we can also consider as a graph, as a complete graph where each point has an edge to any other edge, which is given by the distance. You cannot read, right? Sorry. I wrote it builds and truncates the minimum spanning tree, which often is abbreviated as MST. All right. So I'm going to draw it here. The minimum spanning tree. It is spanning, that means it is a subgraph of your full graph where each node is connected to any other through that subgraph. That's spanning. It is minimum in the sense that the sum of the edge weights used to construct the subgraph shall be minimal. And such a minimal graph is always a tree. because you see here the points are already connected. Now, sure, I could make a shortcut between 2 and 10, but this would add to the weight of the graph, and 2 and 10 are already connected, so there's no point. So this is the minimum spanning tree. And so in this example here, I said that the edge weights between any 2 points are given by the distance between those 2 points. And if I truncate this minimum spanning tree, it means I eliminate all edges larger than some threshold. You know, as I've done here before, I truncate it here. So these were above the threshold, and I end up with the 3 clusters that we see here. And talking about beauty of algorithms, okay, Gaussian mixture model scales ranks highly in Manuel's system. This one ranks highly with me because it's actually an interesting combinatorial optimization problem, which happens to be a very easy one. So minimum spanning tree, if you write it down as an optimization problem, it's not immediately obvious that it can be solved so efficiently. And yet, the greedy algorithm that we've been following here, we looked at edge weights of increasing length and added them as long as it did not create a loop. This is one of the very simple, efficient algorithms that solve this optimization problem globally. This is actually called Kruskal's algorithm. Just out of curiosity, who studied Priem's and Kruskal's algorithm before? Okay, thanks. And there are other algorithms to find minimum spanning trees. Good. So this is single linkage clustering. It's very computationally efficient. It does have a drawback, and it's so good. It's easy to understand. It's easy to implement. It is fast. However, it has a property which in some data sets makes it perform not so great. So what I try to insinuate with this picture here is that we really have 2 clusters. Unfortunately, if I have a little bit of noise in between those clusters, then unless I'm lucky and I can tune the threshold very precisely, then my minimum spanning tree will build a nice bridge between these clusters, and then they get connected even though I think there should be 2 clusters here. Okay, so noise can bridge, or sometimes in literature this is called chaining. It can chain clusters. All right, this was single linkage. Any questions about this? Okay. Then the opposite of single linkage clustering in a way is complete linkage clustering. It works much the same, except that where previously we had an argmin, we now use an argmax. So if I'm considering here 2 clusters, cluster 1, cluster 2, I'm looking at not the minimal distance between any 2 points in the cluster, but the maximal distance. So maybe I can draw a picture here. I'm recycling this picture here. So the minimal distance, if I say that this here is C1 and that is C2, the minimal distance between these clusters was that. So that was the minimal distance between any 2 points. That's what used as criterion in single linkage clustering. And complete linkage does the opposite. It looks at the sets of points that are furthest away. So let's say this one and that one. Check. That gives me the maximal distance, or the and is being used in the complete linkage clustering. All right, now what's good? Excuse me, good. It's easy to understand. It is not quite as fast as single linkage clustering, but still fast. Can you think of what can be good or bad? What kind of clusters is this complete linkage going to form? Or what clusters will it break up, even though we would like them to be single clusters? Yeah?
Very lengthy ones, so like a long line.
Yeah, so this does not allow elongated clusters, or only at very high levels in hierarchies. So if we go back to our let's say we have a cluster here, and we have a cluster there. And if I'm asking complete linkage here to find, if I'm thresholding, if I want to find 2 clusters, it will do something like that. Because the distance here within a cluster from one end to the other is too long, and that's why it's being broken up. So it does not allow elongated clusters, or I could say conversely, it produces compact clusters, which is something that sometimes we want and sometimes we don't want. So the question essentially always is one of, do your prior assumptions, do they match the nature of the data set at hand? Now let's look at this plot. Maybe we can guess here which specific agglomerative clustering criterion they used. Agglomerative clustering is here. And honestly, I don't know. Speak up, please. You think it's what?
If we look at the lowest data set and the square one, you actually have 2 different clusters in the corners of the square. I mean, that's
So there and there, yeah. So it's not complete linkage for sure, or it would not have separated the 2 circles the way it did. So I don't know. Read the docs. All right. But thanks for pointing those tiny spots out. All right. Good. So it's already time for a break. After the break, I want to give you an algorithm that has single linkage and complete linkage and a few others as limiting cases. And then we'll look at more clustering algorithms.